Okay, so this will be chapter 40, talking now about quantum mechanics. And in the last two chapters, we've learned that we can treat light as having both particle and wave nature. And we've also said that particles can have wave and particle nature. So how can we mathematically describe the wave nature of, say, an electron? Well, we use the Schrödinger wave equation to do that, so some heavy mathematics here. We can go ahead and stick a particle inside of a box and say, well, what happens to it? We can go ahead and stick a particle, say an electron, into a well and be able to describe it. And actually I'm going to kind of draw a line right here that might represent the energy that electron has. We can talk about tunneling, which is going to be really important when we talk about nanophysics. But essentially, if we have an electron in the first well and it only has this blue amount of energy, it can jump into this well even though it doesn't have enough energy to jump into it this way, which is what Newtonian physics would require. And so that's what we're going to call tunneling. And lastly, we'll talk about quantum mechanical harmonic oscillator, which we can use to describe molecular vibrations. Now, you may be seeing some things in this chapter that's going to remind you a lot about chapter 15. Well, in chapter 15, we used something called the wave equation to analyze waves on strings. Now we're doing the same thing, only the waves that we're talking about are going to be the waves of particles. And so you'll see something called the Schrödinger equation. Now, before I actually introduce Schrödinger's equation, realize that not everyone here has seen complex numbers before, so crash course in complex analysis. Big credit to Wikipedia for the next several slides. Essentially, if we were to say, you know what, I want to take the square root of -1, we know mathematically we can't actually do that. However, if we define this to be equal to something, and we're going to call it I, then we can be able to evaluate numbers like this, and we would essentially be able to say, well, if we were to square I, then we would get -1. So this is purely a mathematical construct, but it makes solving equations, a whole lot easier. So we can write a complex number, and let's just say that we're going to say z is equal to a plus I times b. This is going to be a number with some real parts and some complex parts. We can often write the real part of this, re of z, is going to be equal to a, and that's just this part right here. And then the imaginary part of z is going to be this part right here, the part that's multiplied by I, and that's equal to b. Now, oftentimes we want to be able to graph this in a real and imaginary plane, and we always put the real axis on the x-axis and the imaginary axis on the y-axis. And so if we were to graph this complex number, z, it would kind of stick off right up here. Now, something that you will see is the complex conjugate, which is going to be a z star, and that's going to be equal to a minus I times b, where essentially you go through and you replace any I that you see with a negative I, or a negative I with a positive I. And this guy would kind of extend right down here, and this guy would be z conjugate. Now, if you're looking for a physical meaning for this, then you can scour the internet just like I did. This is purely a mathematical construct. Now, what complex numbers buy us is they buy us solutions to equations that would have no solutions in a real-world sense. If you were to think about this guy right here, obviously it's not going to have any real solution because we're going to end up with the square root of -9. However, if we were to be able to define the square root of -1 as I, then you could realize that this thing is going to have solutions. There's going to be two solutions, and they're going to be -1 plus 3i and -1 minus 3i. And you can stuff those back into the original and prove that, hey, these numbers do actually work. Now, the fundamental theorem of algebra is perfectly cool with us doing this. Now, a fellow by the name of Euler came up with a really important relationship that allows us to write exponentials as sines and cosines using an imaginary component inside of the exponential. So this is really, really, really important. If you were to look at the real and the imaginary plane and think of it just a unit circle, then you could kind of pick your A and B points on there. And what Euler came up with is he came up with this relationship right here that allows us to write, again, the exponential with an imaginary component as having a real and an imaginary component. And this will in turn allow us to write the sines and cosines as being functions of exponentials. Now you can kind of see that if we were to define the same z as we did before, only now we're talking x's and y's, that it's going to have the x and the y, the a and the b components, and we can write that guy as such. And we can write the complex conjugate, the z star. Wikipedia uses a bar, but that's okay. Again, just replacing the I with a negative I, we can write it as such. Now, with a little bit of work, we said that the cosine is going to be the real component of e to the I theta, and the sine would be the imaginary component. With a little bit of work, you could convince yourself you could also write the cosine as the sum right here, and the sine as the difference right over here. And again, the sine is going to be the imaginary component, so you have that little I right down there. And again, this is going to be really, really, really important for this chapter. We can, of course, add or subtract the two above formulas and get what we would expect for e to the I x, or e to the I theta, and e to the negative I theta, where here we've taken into account the fact that sine of negative x is going to be negative sine, and cosine of negative x is just going to be cosine of x. Now, on a unit circle, you can kind of see how these guys work out. That would be e to the ix, and this would be e to the negative ix, and it kind of falls along a straight line with this guy right over here, and the sines and the cosines are all kind of interrelated right here. Now, you may recall from chapter 15, I know that was a long time ago, that we were talking about waves on strings, and essentially we said a wave moving in the plus x direction could be written as such, and we can do a little bit of rearranging here where we had the angular frequency was 2 pi times the regular frequency, and k was related to the frequency and the mass. And it turns out these guys were solutions to this second order differential equation, which was known as the wave equation. And I realized that most people hadn't seen second order differential equations yet, and so I kind of glossed over it. But these guys were solutions to this guy right here, and that's going to be really important as we move into this chapter. If you're feeling a little bit dicey, you could take the second partial and stuff it in right over here, and then you could go ahead and take the second partial with respect to time and put it in right here, and convince yourself that this equation does hold and this is a valid solution to the wave equation 15.2. So this is what Schrödinger's equation looks like in one dimension, and this is going to be really important because we're going to generalize to 3 dimensions in a little bit. And essentially the book goes through a big long scary derivation, but much like waves on a string must have obeyed this second order differential equation in chapter 15, then a free quantum mechanical particle must obey this equation right here. And very typically we say that a wave function psi, which is a function of x and t, is going to describe that particle. And what we kind of have is we have h bar squared, 2 times the mass of the particle, the second order differential with respect to x, and here we have an I, and there's another h bar, and then we take the partial with respect to time. And this is going to allow us to determine the wave function of that particle, which is going to contain all of the information about that particle that we need to know. Now, keep in mind that the presence of I in this equation means that these wave functions are going to always be complex functions, so this is a little bit different than what we saw in chapter 15. Now, if we were to take the square of the absolute value of the wave function, that's actually called the probability distribution function, and it tells us the probability of finding some particle near some position x, say in some region x plus delta x, at some time t. Now when we go ahead and we evaluate this guy, so just like, I'm not going to write the x and the t, then when we go ahead and we evaluate the absolute value squared, this is actually going to be equal to psi star multiplied by psi, so it's actually going to be the complex conjugate. Now the reason why we have to do it like that is because psi by its very nature is going to be a complex number, and so when we go ahead and we square this guy, we need to kind of take that into account. Now, before I scare you too much with some really kind of heavy mathematics, keep in mind that Schrödinger had a cat as well, just kind of a theoretical cat. But what he said about this wave function, this guy psi, is actually it's going to be a superposition of all possible wave functions until we can make a measurement. And so his little thought experiment said, suppose I had an isolated system right over here, and this box, inside of this box I have a cat, and I have this little radioactive device, and we know that it's going to emit some radiation at some point. We don't know exactly when. And then we have this little Geiger Euler tube that could go ahead and measure that radiation, and when some radiation finally hit it, then a hammer would fall and smash this vial of poison, and it would kill the cat. But until we actually made a measurement of this cat's wave function, then this cat's wave function is going to be a superposition of both a dead cat and an alive cat. So the cat could be both dead and alive at the same time. Now, the solution to this is pretty straightforward, at least in one dimension. We know that this equation will have a solution that looks like this, where this is the wave function, and you can prove yourself that this is a solution by sticking it into the other second order differential equation. Now, a couple things about this k and this omega, the angular frequency and what we called the spring constant earlier. This is going to now be related to the momentum and the energy, and if you remember that the momentum should have been equal to Planck's constant divided by the wavelength, then that's essentially the equivalent of saying this guy right here. So that's going to the k value is going to be related to the momentum, and because the energy is going to be equal to h times the frequency, and the frequency is 2 pi times the angular frequency, then that's where this guy comes from. So the angular frequency is related to the energy. Now, a couple things to kind of keep in mind. The interpretation of this wave function is not very straightforward, and one of the things that it kind of represents is the wave function is going to kind of represent the distribution of a particle in space. When we want to try to find it, then take a look at the probability distribution function. So let's go ahead and figure out what psi star ought to be for this guy. It's got to be equal to a e to the negative I kx, and then e to the plus I omega t. If we wanted to find out what the probability of finding this thing was, then we can say, okay, well, this has got to be equal to psi star multiplied by psi. I forgot my squared right over here. And you can actually go ahead and convince yourself, when you multiply all these guys out, that we're going to have a times e to the negative I kx, and then e to the plus I omega t. Keep in mind I have implicitly assumed that a is real here, and we pretty much always will, multiplied by a e to the I kx, and then e to the minus I omega t, that this guy is going to cancel out with this guy, and then this guy right over here is going to cancel out with that guy, and the probability of finding this thing is just going to be equal to a squared, which says I have an equal probability of finding this thing anywhere, and this is independent of time. And that would kind of be the definition of a free particle. Like, it could be virtually anywhere. It's not until we start putting boxes around it that we have chances of finding it somewhere. Now, kind of graphically, what does the real part look like? The real part's going to look like a cosine. It's just going to go up and down, up and down, up and down. And the imaginary part is going to look like a sine. And think back to some of those relationships for Wikipedia that I showed in the first couple of slides. Now, both of these are evaluated for the time being equal to 0 right here and right here. So let's take a quick look at example 40.1. Suppose we had two free particles in space, then we can actually just superimpose their wave functions. So I'm going to say that the wave function is going to look like these two guys right over there. Let's go ahead and prove that this is a valid solution to the Schrödinger equation. And for once, you see I actually put the problem in here because I don't want to write all this in. So we've just taken that wave function, we've put it right down onto the left-hand side of the equation, and we've the book goes ahead and it evaluates that second order partial, and you can kind of see that it's going to work its way out to be looking like this. On the right-hand side, we're going to take the partial with respect to time, multiply it by I and h bar, and these two guys are going to be the same, and since check and check, this is a valid solution to the wave equation. I highly recommend seeing how the book finds out the probability distribution function for psi simply by taking psi star multiplied by psi. Now we did see that a free wave kind of existed, or had the possibility of existed anywhere. Now how can we get something that has a more localized location in space? Then what we kind of have to do is we just have to say, okay, well, we can superimpose a whole bunch of different states that have a definite momentum and energy, and that would kind of look like this, where I've taken a whole bunch of sines and cosines, and it has some amplitudes which will depend on the k, and we're just kind of adding these guys up from negative infinity all the way to infinity, and that's going to give us a wave packet that exists in some region in space and in some region of time. And to make the wave packet more localized, then we just have to increase the range of momentum and energies it must include. And kind of the reason for that is because the delta in momentum times the delta in x must be larger than or equal to h bar over 2 pi, so Heisenberg's uncertainty principle comes back once again. Now, if we were to look at the probability distribution function at some given time t, now this guy right here will have some peak, and that's going to be kind of like the most probable place to find this particle or this wave that we're looking for. Now, one thing to keep in mind about this probability distribution function is all of them do have to be normalized, and so what we kind of do is from negative infinity to infinity, we have to normalize this psi squared term relative to dx, and essentially that's going to dictate the a terms or the a terms if we have more than one of them. There we go, equal to 1.